and thanks to the organizers for inviting me. So with this talk, I wanted to give a brief overview of how my group and I are trying to rethink mid-ocean ridge models and think of seafloor spreading not as a continuous process, but as a sum of discrete magmatic or tectonic events, hence the playful title. And this is work that is supported by an ERC grant that is just started this summer. So let's start broad with looking at a cross-section across the Atlantic Ocean right here. You can see the familiar roughness of the seafloor, which is commonly interpreted as the signature of fault-bounded abyssal hills. So the nature of the seafloor in a slow-spreading ridge environment is basically, let's say, about 20% fault surfaces here, making the relief, and the remaining 80% is essentially basaltic, ultimately covered with sediment. And this structure traces back directly to the way the seafloor is being accreted by some component of magma emplacement and some component of tectonic faulting. So in a bit more colorful and cartoony view, what happens at the mid-ocean ridge is that you have mantle upwelling that's driven by the separation of the plates. This induces adiabatic decompression melting, magma focuses to the ridge axis, and some of it makes its way into the brittle, shallow lithosphere. But apparently, not all of it manages to keep up with the extension, and faults do have to do a little bit of work to take up the remaining extension. So that's kind of the common way that we understand the way these seafloor landscapes are shaped, and nicely symmetric ridge segments. But it also shows a lot of variability. So this is a place, for example, at 14 North in the middle of the Atlantic. But if you swim just 50 kilometers to the south, the structure looks a bit different. You see these dome-shaped exposures of mantle, which are the signature of larger offset faults bringing mantle all the way up to the seafloor, which attest to a lessened contribution of magmatism and a greater contribution of tectonics to shaping that seafloor. And so the standard way to understand these different regimes of seafloor spreading is how much magma manages to make its way into the brittle lithosphere. So when you have lots of magma into the lithosphere, you don't need much faulting, and vice versa. And this is a paradigm that has been developed by Roger Buck and collaborators over the years. It has some limitations, however, because as we can see, there's often enough magma being produced below the ridge to account for a 6-kilometer thick oceanic crust. So a very basic question is, if you've got that much magma around, how come you don't do mid-ocean ridges that are 100% magmatic? What is it that prevents all the magma to be emplaced at shallow levels, and why do we need faults in the first place? Or maybe a more focused way of asking this question is, effectively, what sets this time average rate of magma emplacement that accommodates stretching into the lithosphere? Up until now, this has mostly been imposed in numerical models, and we've been lacking the physics to explain what sets that time averaged intrusion rate. So the approach that we've taken recently is to reconsider seafloor spreading not as a continuously widening dike and continuously slipping faults, but for what it really is, which is the succession of discrete events. If you look at ophiolites and exposed structures of oceanic crust, it's very clear that through these dikes, cross-cutting dikes, the quantum event of magmatic accretion is the emplacement of a meter-wide magmatic fracture, whereas the quantum event of fault growth are these increments of slip that can be seismic, but can also be probably, to a largest extent, aseismic. And so the view that we're moving towards is, well, I can stretch the axis of a ridge by plate divergence. I've got a fault that can decide to slip or not to slip, or do an increment of slip. I also have a magma plumbing system that's providing magma to shallow levels. When is it going to be favorable to intrude that magma by diking and accommodate extension that way? Or when is it going to be favorable to slip on that fault? So the first question we need to answer if we want to tackle these kind of short-term views of seafloor spreading is, how is the axis stretched? Essentially, how do these black arrows on the sides work? We've got one really useful data point from the Juan de Fuca Ridge from an experiment by Chadwell and Spies in 2008, who did what's called GNSSA measurements. They essentially measured the position of precision transponders on the seafloor relative to the ship with acoustic techniques, measured the position of the ship with GPS, and were able to show that this point on the plate, which is about 25 kilometers from the ridge axis, is moving at the full plate rate. Another way to see this result is in a cross-section across the ridge. With prior geodetic experiments, we've known that there isn't a lot of stretching on a kilometer scale at the axis of the ridge, But we also know, thanks to that GNSSA measurement, that about 25 kilometers onto the side, you're already part of the rigid plate. That means that there has to be some kind of horizontal stretching from this plate on the left to this plate on the right that's distributed over a characteristic distance that's less than 50 kilometers. That's the conservative estimate. Order of magnitude, it's reasonable to think it's on the order of 10 kilometers. So we can translate that into a stretching rate and ultimately an extension stress buildup rate. So that's, again, what's represented by the black arrows. And if we think of how the dikes or faults might be loaded by this stretching, well, a very simple, naive view would be to say, my elastic stretching gives rise to an increase in deviatoric stress, horizontal deviatoric stress through time, until I meet some kind of fault slip threshold, can be seismic, can be aseismic, at which point I will have an event and a stress drop, and the cycle will repeat. This is the simplest possible view of an earthquake cycle. But of course, things are a little bit more complicated because you have dikes that enter the equation. What if the diking threshold happens to be lower than this faulting threshold? Well, in that case, the axial stress should build up to the diking threshold. You'll have a stress drop due to diking. And then when you build stresses again, you should dike again. And so your ridge should be 100% magmatic. On the other hand, if the diking threshold is above the faulting threshold, you're going to be 100% tectonic. So one straightforward way to reconcile both types of events is to invoke a diking threshold that fluctuates through time. And one way that we thought about to do this would be to invoke the buildup of magmatic overpressure in the shallow melt lenses that we see at the axis of magmatically robust mid-ocean ridges, which Milena is going to talk about extensively in the next talk, I'm assuming. And effectively, when you think of magma building up, accumulating in replenishing magma pockets at a shallow depth, it should have some effect on loading the lithosphere above. I won't go into the details, but there are ways that this increase in magma overpressure translates into stress changes in the brittle lithosphere that facilitates tensile failure as opposed to shear failure here. So we might end up in a situation when we alternate between phases where a faulting event is favorable and a phase where a diking event is favorable. So for example, here, I'm stretching the axis up until an earthquake, that's the white star. I have a stress drop, then I stretch again. But during that time, the magma chamber has inflated so much that at that point, it's easier to trigger a dike than to slip on the fault again. I have a big stress drop from the magma drainage, which translates to a diking threshold that goes all the way back up. Maybe I have time to slip in an earthquake in the meantime, then an eruption, et cetera, et cetera. And so in that very simple toy model, or simple framework, the time averaged M value would just be the ratio of the number of intrusion events to the total number of events. And you can see that that number is going to be strongly modulated by the rate at which the lithosphere is being stretched. So it has to do with the axial loading rate, the spreading rate, and the distribution of the interseismic or interdiking strain, but also the inflation rate of the axial melt length, which describes how quickly this red arrow can come down. And of course, whether these events interact with one another and their respective stress drops will also play a role. So how quickly can mid-ocean ridge magma lengths actually inflate? Well, we don't actually see them inflate per se, but what we see is seafloor upwelling in between eruptions. So perhaps the most famous example of this is that axial seamelt, which is a hotspot boosted mid-ocean ridge section on the Juan de Fuca Ridge that has been instrumented for more than 20 years, and where we've seen several cycles of eruption with seafloor going up by several meters, sudden subsidence during an eruption, uplift again, drop, and uplift again until the next eruption, which could be any day now. And another place where we have similar observations, though a bit more indirect, are the East Pacific Rise at 9°50 north, where we know there's a magma body that's been well imaged by Milena, among many others, but Milena has done very beautiful work recently on characterizing the details of the geometry of that plumbing system. And here at the East Pacific Rise, we know that in about 2009 to 2012, there was active inflation at the seafloor. So maybe 4 years after the last eruption, we knew the seafloor was going up by 7 centimeters per year at the most, which is something we can explain if the melt length at 1.5 kilometer depth is continuously being replenished by addition of magma by 150 cubic meter of magma per meter along the ridge every year. And that's consistent with the time average rate of magma that you need to build the upper crust. So very reasonable number. So Okay, so that's indirect evidence that there's magma being added into the melt lens. That should be expected to trigger, like I said, some stress changes in the lithosphere above. We can see, for example, how the melt lens inflation pressurizes the base of the lithosphere with the color scale by something like a megapascal every year if you want to fit these observations. And that is not something that we can easily infer directly. However, one thing we have at EPR is black smokers. So a very cool project that we've been working on with Thibaut Barrère, Milena, and our co-authors from the US are funded by a big NSF project is looking at time series of black smoker temperatures over the last 35 years at EPR. And what we see is that there was an eruption in 1991. After the eruption, the black smoker vents were at about 360 degrees, and they've gradually become warmer until the next eruption, which happened in 2005 or 6, up to 390 degrees. Then they appear to cool down a bit. We have a lack of data around 2010, 2015, but recently they've become almost as hot as they were before the last eruption. And spoiler alert, there actually was an eruption, which you can read about in the New York Times a couple months ago. So we do think that these fluctuations in venting temperatures do capture something about the deformation associated with magmatic cycles. And to go real quickly on this, one way we can explain why the temperatures are getting hotter is to invoke a drop in permeability of the upper crust. A steady drop in permeability of the upper crust slows down the fluids, makes them get warmer because they're trying to transport the same amount of heat by going slower. And one straightforward mechanism for slowing down the fluids and reducing the permeability is, again, to invoke this pressurization of the base of the lithosphere by an inflating magma lens. And if we run the numbers, it turns out that a pressurization of the AML by about a megapascal per year would be what you need to explain these long-term time series. So again, at EPR, we don't have the continuous seafloor geodesy like axial, but we have black smokers, and they're probably telling us something interesting and usable about this system. So to wrap it up, back to my broader question, through these indirect seafloor geodetic constraints or direct seafloor geodetic constraints, we can place a number on what we think the pressure rate is associated with the AML inflation. And so we can place constraints in the toy model on how quickly that red line should go down. So how quickly it becomes easier to dike than to fault. We can combine that with all the other observables that we need to close the system of equations. So mainly we need a proxy for the thickness and the strength of the oceanic lithosphere on axis, which we can get from the depth of the AML itself or from the depth of microseismicity. And so we can get a hot end member, a thin lithosphere end member, and a cold, thick lithosphere end member. And we can use this data, the lithosphere thickness across spreading rates and the melt lens pressurization rate across spreading rates with just one data point interpolating linearly across all the spreading rates, just to keep things simple with the lack of data. And if we do that, we can actually work this into our model framework, which we published in 2020 with Pierre Dublanchet, and show that this variability in pressurization rate coupled to the variability in lithosphere thickness can actually explain the long-term estimates of M, of magmatic fraction, as inferred from the symmetry. So essentially the fact that as slow spreading ridges, you see M's that are kind of all over the place, from 0.8, 0.9 to 0.5, where you have detachments. At intermediate rates, you go up to M's of 0.8, and you go all the way to M equals 1 at the fast end member. So that's still a toy model, but it's a nice proof of concept to say that there might be useful things to learn in the short-term interactions between dike intrusion events and fault slip events on human timescales, which are directly observable, and the magmatically accommodated fraction of the plate separation that we can read in seafloor bathymetry. Of course, there's still a long way ahead to fully achieve this. So we need to answer a bunch of specific questions that have to do with all the individual ingredients of the system. And that's what I've set out to do with this starting grant. So how does the AML actually replenish? What's the mechanism to pile up magma in this reservoir? How do the axial stresses actually build up between events? What's a good triggering criterion for a dike? And should we rethink this idea that events are 100% tectonic, 100% magmatic? We know that when a dike propagates, it triggers seismicity on adjacent faults. So probably we'd have to consider hybrid events that are a mix of both. And so the big the big question, which is probably for several decades in the future, is how can we properly upscale from the human timescales to the geological timescales? And for that, stay tuned. Maybe I'll have an answer in 20 years. Thank you.